I'd like someone to use the word Jimmy in a sentence.
I take it you don't mean the name.
You are right.
Okay, here it is. The burglar used a jimmy to open the window.
Uh-huh. Now, do you all know the word Jimmy in that context?
Yeah, it's a tool used to get into someplace.
Just where is this conversation going, Frank?
Well, we have been talking about the tools of mathematics. So now we're going to talk about ways to use those tools to get into difficult places. And if we were burglars, we would use a jimmy. But since we are intellectuals, we are going to use a James. No, it makes sense now. We're going to use our intellectual Jimmy, our James, to get inside some difficult math ideas.
Just what does this James look like?
Well, it all depends on how you look at things. Now, the first thing that you have to do in real life, when you read about or hear about a problem, the first thing you have to do is build a picture of it in your mind, a mental picture, right? Okay, now, do you all remember this?
Oh,
That's Todd's
yes.
dumb fish problem.
No, this isn't a problem. This is a picture of a problem.
Frank, are all problems that fishy?
Well, I don't know about that, but I do think that most of the problems you're going to encounter in life are a lot less complex.
Good.
All right, now once you have the picture, then you can begin to assign the variables.
For the unknowns, such as head, H for head and T for tail and B for body?
That's right, absolutely. And we've generally used X or N for the things that we're looking for, right? Okay, now after you have done that, assigned the variables, then you can begin to work the problem with the numbers that you already know the answer for. Now, just those 3 steps, build a mental picture, assign the variables, and solve with numbers that you already know. Those 3 steps, with those 3 steps, you can solve 90% of the problems in the world.
That's it?
That's it. For instance, I know a man who is 3 years older than twice his son's age. Well?
There's not enough. There's no question.
Well, now, do you suppose there's only one man in the world that is 3 years older than twice his son's age?
Heck no, there are millions of people like that.
Well, then let's use our James to solve the problem and find out about all of them, all right? Now, what is it that we want to know?
Maybe the father's age, maybe the son's age.
But the ages are dependent upon each other.
That's right. That's right. Let's look at a picture of this situation, all right? Now, how about this?
Well, that would be son's age twice plus 3 years.
All right? All right? Now, this is the picture. Now, what do we want to assign the variable to?
Well, let's call the son's age X.
All right, let's do that. Let X equal the son's age.
Then we can say 2 times that plus 3
2x plus 3.
would be the father's age.
All right. Now what?
Well, if we find out what X is, multiply it by 2, add 3, then we'll know the father's age.
There. Now you see, we're already beginning to use our James.
Well, if you knew the age of either, then you could find the other.
That's right. That's exactly right. This is the right James for this problem. All right, now here's your picture. Here are your variables. Who can assign some values to the variables?
Well, I can. If the son's age is, let's say, 10,
All right.
then the father's age would be 23. That works. 2 times 10 is 20, then add 3, 23.
Yeah, it works, Martha, but the father would have been 13 years old when the son was born.
Possible.
Well, all right.
Okay.
And what would you have if the father was 45?
That's more like it. In that case, the father would have been 24 when the son was born.
Well, now wait a minute. I don't know if this is important or not, but it seems whatever age we say the son is, the father would be 3 years older than that when the son was born.
Yes. Now, that would be important if the question had been, how old was the father when the son was born? Now, what would a picture of that look like?
I think I could do that one. It would start off looking like what we've already got up at the top there.
All right, I'll draw what you say.
Okay, the son's age and the son's age again, that's 2 of them, plus 3 years. And because we want to find out how old the father was when the son was born, we need to subtract the son's age.
All right. You mean like this.
Yeah, I think that's it.
But as that is, well, you could just get rid of one of the son's age circles because you're adding one and then subtracting one.
Uh-huh.
Well, then that would mean the son's age now
X,
plus 3
yes.
would have been the father's age
2x plus 3.
when the son was born. Well, that's what I said.
You know, assigning these variables gives some people trouble. It's almost like translating things into a foreign language.
Now, so I can relate to that.
All right, now suppose that I make a statement in English and you tell me what the algebraic statement is. Okay, here's an example. What is some number increased by 12? That's x plus 12, right? Everybody follow? Okay, now then, we will always use x for the unknown. All right, here's the first one. 3 more than 2 times some number.
That's the father and son problem. 2x plus 3.
2x plus 3. That's very good, Bill. Very good. All right, now how would you say this in algebra? A number times itself minus 7.
Well, that would be x times x minus 7, or probably x squared minus 7.
Oh, all right, Sue. Very good, very good. All right, try this one now. Okay, half of some number decreased by 9.
That's 1/2 x minus 9.
1/2 x minus 9. Yes, but there is another form for it.
How about x over 2 minus 9?
All right, all right. You folks are getting ready for the big time now, okay? All right, now pay attention to this one, all right? 2/3 some number less 1/8 that number.
Well, how does this sound? 2/3 x can be written 2x over 3, and 1/8 x is the same as x over 8. So that's 2x over 3 minus x over 8.
Yeah, doesn't that look good? That's real impressive looking, don't you think? Okay, here is another one. 6 times this number equals this number.
6x equals x.
Now, would anyone like to try to substitute a value for x?
Sure. How about 0?
How about 0? All right, good, good. Now, here are some worksheets, and these examples on here are just like the ones that we've just completed, okay? Now, try to draw a picture of the problem, and then make a literal statement, that's in letters in English, and then tell what you would need to know and what you need to do in order to make a numerical statement, okay? Now, we'll work on these for a little while, and I'll just kind of wander around and look over your shoulder. You want to pass these out?
This is Steve Wise again, here to help you sort out some of the most important points in this scene. The James, the mental jimmy that allows you to get inside some pretty tough math problems, works like this. First, you build a picture in your mind of the way the problem works. Go through the problem from start to finish so you can understand each part and draw a picture of it. The question, the thing you want to know, is usually at the last of the statement. Next, you assign variables to the parts. Use letters to represent those relationships that the story suggests. Once you have done this, work the problem with numbers that you know the answer to already. If they work, so will the more complicated numbers in the problem. Look at this example. Words are important to you when you want to write an equation for a given situation. Here is a list of statements that you will often see, and each is followed by its algebraic expression. 6 less than something, x minus 6. Something less than 6, 6 minus x. 4 times as much as something, 4x. 5 more than something, x plus 5. 5 more than twice something, 2x plus 5. 20 increased by some number, 20 plus x. Some number increased by 20, x plus 20. Some number decreased by 9, x minus 9. Sue's age 14 years from now, x plus 14. Bill's age 10 years ago, x minus 10. As you use the James to get inside story problems, you will learn many other word phrases and how to write them in the language of the mathematician. There is a longer list in your workbook. Study them when you have time.
Well, you folks are definitely getting the idea of using the James. If you can draw a picture of the situation and then assign the variables and get the operations right and then work it with the numbers that you already know, nothing can stop you.
Provided you do the arithmetic right.
True, true. But you are all becoming excellent calculators.
Oh, I think I can relate to that one.
However, very often you're going to find that there are problems within problems, and then you have to use the James more than once. Now, take a look at this problem. A man had a cylindrical tank that was 4 feet across and 3 feet deep. How many gallons of water would it hold? Sue, what do you make of that?
Can I draw a picture of it?
I wish you would.
Okay. Well, the cylinder would look like this.
Good. Good. Now you have the first part of the James. You've got the picture.
Okay.
Now we need to know the volume of the cylinder.
All right. Now, does anybody know how to do that?
I can look up the formula.
All right.
It says the volume of the cylinder is pi times the radius squared times the length.
Okay. Now, who can help Sue substitute the values?
Well, the radius would be 2 feet since that's half of the diameter.
And the length will be 3 feet. It looks like the height, but I guess you can call it the length.
And we all know that pi is equal to 22/7.
Good. All right. Now, before we calculate this, what kind of units are we going to get as an answer to this problem?
Cubes. Volume is figured into cubes of a certain size that will completely fill up a space. So since these dimensions are given in feet, the answer is going to be in cubic feet.
Now, Todd, I trust that you will accept this cylinder being filled with cubes even though they don't fit.
Whatever you say, I learned my lesson.
Good, good. All right, let's solve it then.
Okay, then the volume would equal pi, which is 22/7 times the radius squared, which will be 4. 2 times 2 equals 4.
Good, good.
Times the length, which is 3.
Huh.
Which would be 22/7 times 12 over 1, which equals 264 over 7.
Good.
You divide by 7. So the answer I get is 37 5/7 cubic feet.
Very good. Now, do you all agree with that?
Yeah.
Okay, then we're all done. No?
Well, we need to find out how many gallons are in 37 5/7 cubic feet.
Oh. Any ideas?
It says in here that you multiply the number of cubic feet by 7.48 to get the gallons.
All right, let's do it then.
Oh, wait a minute. I should have done this by decimals instead of common fractions. It would have been easier.
Sue, I'll convert the 5/7 to a decimal.
Martha, I think we need your calculator now.
Well, I got it right here. You want to use it?
Yeah. Huh? Thank you. Okay.
Okay. Let's see, the decimal to the nearest hundredths would be 0.71.
Wait a minute. I've lost track of things. What was that number again, Bill?
It's 37.71. That's the number of cubic feet in the cylinder. Times 7.48.
Okay. Okay.
All right. Now, does Anyone besides Bill using Martha's calculator have an answer here?
I get 282.0708.
All right, does everyone agree with that?
That's it.
Is that what you've got?
Perfect.
All right. All right, now what does that number tell us?
Oh, I've forgotten.
That tells us the number of gallons in a cylinder that is 4 feet wide and 3 feet deep.
Now, do all of you see that? All right, good. Now, why don't we just review what has transpired here? Sue, you did an excellent job. Now, who can explain each part of the James?
Well, first, we found the volume of the cylinder according to the formula for that shape.
Uh-huh.
And then we converted cubic feet to gallons by multiplying by 7.48.
Well, I'm impressed. I really am impressed. I mean, you have just jammed your way through a very complex problem. Very few problems that you're going to run into in life are more complicated than this one. You know, I really believe that you can solve any problem that you can draw a picture of. Even this fish problem will work if you use the James. First, you draw a picture of the situation in your mind or on paper, and then you assign the variables, and then you solve the problem using the numbers that you already know. All right? And then you'll come up with a numerical fish. All right? Let's go home.
Ah, gosh. Bill?
There are several important things you should have picked up in this scene. In everyday practice, problems are word problems. They are stories that have numerical equivalents and solutions. More often than not, the story itself doesn't give all the information needed to find the solution asked for. You may need to look up a formula or a conversion function. One important part of the scene may have slipped by you. One of the students changed a common fraction to a decimal using the proportion process we've discussed so many times before. Here's how that works. In her mind, she was saying 5 is to 7 as something is to 100. By cross-multiplying, she found out that 714 thousandths is the same fraction family as 5/7. Proportion is a very valuable tool. Be certain you know all about it. Last, Frank has made such a big deal out of the fish problem. Look at this diagram again. Maybe you will begin to see how all the pieces go together to tell how long the fish is.
But Frank's not even here. Frank's
He
late.
probably
Going on 8 o'clock.
Probably deserted us.
I hope he's going to give us that test.
That's what
Oh, here he is.
Hey.
Hey, what is he? Uh-oh.
Well,
What is that?
now this is an evening some of you thought would never come. Our last class.
I think it's sad.
Yes, it is sad a little bit because we've been through a whole lot together. However, I do have a little going away present for you.
It's that long-awaited exam, isn't it?
You got it. But before we begin, Sue or Bill, do you want to make your announcement?
Why don't you make it?
We're getting together after class over at Tony's Cafe. We're going to have a little get-together. You're all invited. And, best thing of all, the whole thing is on Frank.
Yay!
On me?
Well, you owe us, Frank.
Oh, he's
Af-
kidding. It's no big deal. We're just having a small celebration in Tony's party room, and we'd like for you to be there.
Well, it sounds like a great idea to me. Okay, let's get started, all right? Now, this exam is in 2 parts. So, you just give me your solution to these 2 problems as you leave, and then I'll meet you all over at Tony's when I've collected them all. Okay? Now then, I am using Todd's fish problem because it is a classic example of the use of inversion and substitution. This can serve as a model to solve lots of problems. All right. Now this other one, this will make you real proud of your perception. Okay? Good luck. Well, Todd, looks like it's just you and me.
Looks like.
Why don't we try to catch up with the others?
Okay. You know, I can't believe I had such a hard time with that second problem.
Well, you sure worked on it hard enough.
Todd, Bill needs to see you in the back room.
Now, Frank, we've all gotten to know you and each other in this, I don't know how long, but all those class time hours and all those health sessions on your free time, I might add. We just wanted to say that we really appreciate it. And so we have a little token of thanks. Tom, Bill, the unveiling, please. It is 58.5 inches long and autographed by all of us.
Oh, my. 58.5 inches long, huh? You rascals, you knew the answer to that fish problem all along.
After you mentioned it every class period, we thought we better learn it.
Well, this is really very nice of you. It's very thoughtful. I'll mount it in my den. Thank you very much. Let's have some cake.
That's done. You know, I know you didn't have a lot of trouble with the fish problem, but how in the world did you get that second one so quickly?
Oh, man, that was an easy one.
Easy? Took me a half a dozen sheets of paper to get that one
Todd,
done.
I can't believe you were the person who told me how to work. Remember that day on the tennis court?
Yeah?
You told me that the diagonals of a rectangle are equal to one another.
Huh?
Think about it. You need a drink.
I mean... Whoa! Let's have some more of that.
Well, the class is winding up. I hope you've enjoyed it as much as I have, and also that you've learned a great deal. There are a couple of ideas from this scene that I need to underscore. Look at the problem that Todd thought was so hard and the others thought was easy. What Bill said was true. Both diagonals of a rectangle are the same length. By merely drawing the other diagonal, most of the students could see immediately that x was equal to the radius of the circle, 10 inches. Todd may have thought of that too, but if he did, he thought the answer was too simple. Now, the message here is clear. If you find a simple solution that's logical, you're probably right. Don't let your increased information get in the way of your common sense. The fish problem, however, is another matter. I would recommend that you study this problem in your workbook until you can see how every step works to make it a model to use to solve other algebra problems. It is solved by using the two most important techniques in algebra, substitution and inverse operations. Follow along as I explain each step of the James in the fish problem. First, draw a picture of it and label the parts. These labels become the variables. Then write it like an algebra problem. The reason this problem is confusing is that there are too many unknowns. You can cut down on the number of unknowns by substituting a different value for the tail in this expression. Since t equals half the head plus the body, that whole expression can be substituted here. The equation says to divide, so we multiply both sides. We multiply again to get whole numbers instead of fractions. Subtract 2b from each side. Divide both sides by 2. Substitute the value for head and body in the expression that refers to the tail. Add the parts and you have the length of the fish. Remember this problem. It will confound your friends. Well, that's it for this program and for our series. I've enjoyed being with you, and I hope you've learned some ways to make math work better for you. Thanks for watching.